Theo, that's annoying because it means that in order to access the value, we need to cast it to its type. Joe, yes and no. Look at our book search use case. We pass all the values along without really looking at their type. The concrete value type only matters when we serialize the result into JSON, and that's handled by the JSON serialization library. It's called late binding. Note: with late binding, we defer dealing with data types as long as possible. Theo, does that mean in my application that I'm allowed to manipulate data without dealing with concrete types? Tip: in DOP, flexibility is increased as many parts of the system are free to manipulate data without dealing with concrete types. Joe, exactly. You'll see late binding in action in a moment. That's one of the greatest benefits of DOP. Theo, interesting. I can't wait to see that. Joe, one last thing before I show you the code for retrieving search results from the database. In order to make it easier to read, I'm going to write JavaScript code as if JavaScript were dealing with I/O in a synchronous way. Theo, what do you mean? Joe, in JavaScript, an I/O operation, like sending a query to the database, is done asynchronously. In real life, it means using either callback functions or using async and await keywords. Theo, oh yeah, that's because JavaScript is single-threaded. Note: for sake of simplicity, the JavaScript snippets in this chapter are written as if JavaScript were dealing with I/O in a synchronous way. In real-life JavaScript, we need to use async and await around I/O calls. Joe, indeed. So I'll be writing the code that communicates with the database as though JavaScript were dealing with I/O synchronously. Here's an example. Theo, in a dynamically typed language like JavaScript, I understand that the types of the values in the list of maps returned by dbclient.query are determined at runtime. How does it work in a statically typed language like Java? And what are the types of the data fields in books? Joe, the function convertJDBC_result_set to list of maps we created earlier, see listing 10.5, returns a list of map from string to object. But JSON serialization libraries like JSON know how to detect at runtime the concrete type of the values in a map and serialize the values according to their type. Note: see github.com/google/JSON for information about JSON's Java serialization deserialization library. Theo, what do you mean by serializing a value according to its type? Joe, for instance, the value of the field publication_year is a number. Therefore, it is not wrapped with quotes. However, the value of the field title is a string. Therefore, it is wrapped with quotes. Theo, nice. Now I understand what you mean by late binding. Joe, cool. Now, let me show you how we store data in the database. Section 10.2. Storing data in the database. In the previous section, we saw how to retrieve data from the database as a list of maps. Next, we'll see how to store data in the database when data is represented with a map. Theo, I guess that storing data in the database is quite similar to fetching data from the database. Joe, it's similar in the sense that we deal only with generic data collections. Can you write a parameterized SQL query that inserts a row with user info using only email and encrypted _password, please? Theo, okay. Theo takes a moment to think about the code and writes a few lines of SQL as Joe requested. He shows it to Joe. Joe, great. And here's how to integrate your SQL query in our application code. Theo, your code is very clear, but something still bothers me. Joe, what is that? Theo, I find it cumbersome that you use _.get of user and string email instead of user.email, like I would if the data were represented with a class. Joe, in JavaScript, you are allowed to use the dot notation user.email instead of _.get of user and string email. Theo, then why don't you use the dot notation? Joe, because I wanted to show you how you can apply DOP principles even in languages like Java, where the dot notation is not available for hash maps. Note: in this book, we avoid using the JavaScript dot notation to access a field in a hash map in order to illustrate how to apply DOP in languages that don't support dot notation on hash maps. Theo, that's exactly my point. I find it cumbersome in a language like Java to use _.get of user and string email instead of user.email like I would if the data were represented with a class. Joe, on one hand, it's cumbersome. On the other hand, representing data with a hash map instead of a static class allows you to access fields in a flexible way. Theo, I know, you've told me so many times, but I can't get used to it. Joe, let me give you another example of the benefits of the flexible access to data fields in the context of adding a member to the database. You said that writing an array of _.get member email and _.get member encrypted password was less convenient than writing an array of member.email and member.encrypted password, right? Theo, absolutely. Joe, let me show you how to write the same code in a more succinct way using a function from Lodash called _.at. Theo, what does this _.at function do? Joe, it receives a map, M, a list, key list, and returns a list made of the values in M associated with the keys in key list. Theo, how about an example? Joe, sure. We create a list made of the fields email and encrypted password of a member. Joe types for a bit. He shows this code to Theo. Theo, do the values in the results appear in the same order as the keys in key list? Joe, yes. Theo, that's cool. Tip: accessing a field in a hash map is more flexible than accessing a member in an object instantiated from a class. Joe, and here's the code for adding a member using _.at. Theo, I can see how the _.at function becomes really beneficial when we need to pass a bigger number of field values. Joe, I'll be showing you more examples that use the flexible data access that we have in DOP. Section 10.3. Simple Data Manipulation. Quite often, in a production application, we need to reshape data fetched from the database. The simplest case is when we need to rename the columns from the database to those that are more appropriate for our application. Joe, did you notice that the column names in our database follow the snake case convention? Theo, I'm so used to the convention, no. I didn't even think about that. Joe, well, for instance, the column for the publication year of a book is called publication_year. Theo, go on. Joe, inside JSON, I like to use Pascal case, like publication year. Theo, and I prefer to have book title instead of title. Joe, so we're both unhappy with the JSON string that search books returns if we pass the data retrieved from the database as is. Theo, indeed. Joe, how would you fix it? Theo, I would modify the SQL query so that it renames the columns in the results. Here, let me show you the query. Joe, that would work, but it seems a bit weird to modify an SQL query so that it fits the naming convention of the application. Theo, yeah, I agree. I imagine a database like MongoDB doesn't make it easy to rename the fields inside a query. Joe, yep. Sometimes it makes more sense to deal with field names in application code. How would you handle that? Theo, well, in that case, for every map returned by the database query, I'd use a function to modify the field names. Joe, could you show me what the code would look like? Theo, sure. How about this? Joe, would you write a similar piece of code for every query that you fetched from the database? Theo, what do you mean? Joe, suppose you want to rename the fields returned by a query that retrieves the books a user has borrowed. Theo, I see. I'd write a similar piece of code for each case. Joe, in DOP, we can use the fact that a field name is just a string and write a generic function called rename result keys that works on every list of maps. Theo, wow, how does rename result keys know what fields to rename? Joe, you pass the mapping between the old and the new names as a map. Tip. In DOP, field names are just strings. It allows us to write generic functions to manipulate a list of maps that represent data fetched from the database. Theo, could you show me an example? Joe, sure. A map like this can be passed to rename result keys to rename the fields in the book search results. So for example, you could write rename result keys like this. Theo, what happened to the field that stores the ISBN? Joe, when a field is not mentioned, rename result keys leaves it as is. Theo, awesome. Can you show me the implementation of rename result keys? Joe, sure. It's only about map and reduce, so I'd do something like the following. Theo, that code isn't exactly easy to understand. Joe, don't worry. The more you write data manipulation functions with map, filter, and reduce, the more you get used to it. Theo, I hope so. Joe, what's really important for now is that you understand what makes it possible in DOP to write a function like rename result keys. Theo, I would say it's because fields are accessible dynamically with strings. Joe, exactly. You could say that fields are first-class citizens. Tip. In DOP, fields are first-class citizens. Theo, how would you write unit tests for a data manipulation function like rename result keys? Joe, it's similar to the unit tests we wrote earlier. You generate input and expected results, and you make sure that the actual results equal the expected results. Hang on, this may take a while. While Joe is busy coding, Theo takes this opportunity to run to the kitchen and prepare 2 espressos. What luck! There's a box of Swiss chocolates on the counter. He grabs a couple of pieces and returns to his office just as Joe is finishing up the unit test. Theo, nice! Joe, do you see why you're free to use rename result keys with the results of any SQL query? Theo, yes, because the code of rename result keys is decoupled from the internal details of the representation of data it operates on. Joe, exactly. Now, suppose an SQL query returns user info in a table. How would you use rename result keys to rename email to user email? Assume the table looks like this. Table 10.5. Once again, the whiteboard comes into play. When he's finished, Joe shows Theo the table. Theo, that's easy. On his laptop, Theo writes the code to rename email. Satisfied, he turns the laptop to Joe. Joe, excellent. I think you're ready to move on to advanced data manipulation. Section 10.4. Advanced Data Manipulation. In some cases, we need to change the structure of the rows returned by an SQL query, for instance, aggregating fields from different rows into a single map. This could be done at the level of the SQL query, using advanced features like JSON aggregation in PostgreSQL. However, sometimes it makes more sense to reshape the data inside the application, because it keeps the SQL query simple. As with the simple data manipulation scenario of the previous section, once we write code that implements some data manipulation, we're free to use the same code for similar use cases, even if they involve data entities of different types. Theo, what kind of advanced data manipulation did you have in mind? Joe, you'll see in a minute, but first, an SQL task for you. Write an SQL query that returns books, including author names, that contain the word habit in their title. Theo, let me give it a try. After some trial and error, Theo is able to nail it down. He jots down an SQL query that joins the 3 tables, books, book_authors, and authors. Joe, how many rows are in the results? Theo goes to the whiteboard. He quickly sketches a table showing the results. Then he answers Joe's question. Because 7 Habits of Highly Effective People has 2 authors, Theo lists the book twice in Table 10.6. Theo, 3 rows. Joe, and how many books? Theo, 2 books. Joe, can you show me the results of the SQL query as a list of maps? Theo, sure. Joe, and what does the list of maps that we need to return look like? Theo, it's a list with 2 maps, where the author names are aggregated in a list. Let me write the code for that. Joe, perfect! Now let's take an example of an advanced data manipulation task where we convert the list of maps as returned from the database to a list of maps where the author names are aggregated. Theo, that sounds tough. Joe, let me break the task in 2 steps. First, we group together rows that belong to the same book, with the same ISBN. Then, in each group, we aggregate author names in a list. Hold on, I'll diagram it as a data processing pipeline. Joe goes to the whiteboard. He draws the diagram in figure 10.3. Joe, does it make sense to you now? Theo, yes, the data pipeline makes sense, but I have no idea how to write code that implements it. Joe, let me guide you step by step. Let's start by grouping together books with the same ISBN using _.groupby. Theo, what does rows by ISBN look like? Joe, it's a map where the keys are ISBN and the values are lists of rows. Here's how that would look. Theo, what's the next step? Joe, now we need to take each list of rows in rows by ISBN and aggregate author names. Theo, and how do we do that? Joe, let's do it on the list of 2 rows for 7 Habits of Highly Effective People. The code looks like this. Joe, first we take the author names from all the rows. Then we take the first row as a basis for the book info. We add a field author names and remove the field author_name. Theo, can we make a function of it? Joe, that's exactly what I was going to suggest. Theo, I'll call the function aggregateField. It will receive 3 arguments, the rows, the name of the field to aggregate, and the name of the field that holds the aggregation. Theo turns to his laptop. After a couple of minutes, his screen displays the implementation for aggregateField. Joe, do you mind writing a test case to make sure your function works as expected? Theo, with pleasure. Take a look. Joe, excellent. Now that we have a function that aggregates a field from a list of rows, we only need to map the function over the values of our rows by ISBN. Let me code that up for you. Theo, why did you take the values of rows by ISBN? Joe, because we don't really care about the keys in rows by ISBN, we only care about the grouping of the rows in the values of the hash map. Theo, let me try to combine everything we've done and write a function that receives a list of rows and returns a list of book info with the author names aggregated in a list. Joe, good luck, my friend. To Theo, it's less complicated than it seems. After a couple of trials and errors, he arrives at the code and the test case. Theo, I think I've got it. Joe, congratulations. I'm proud of you, Theo. Now Theo understands what Joe meant when he told him a cloud is a cloud when they were walking back from the park to the office. Instead of trapping data in the limits of our objects, DOP guides us to represent data as data. Summary. Inside our applications, we represent data fetched from the database, no matter if it is relational or non-relational, as a generic data structure. In the case of a relational database, data is represented as a list of maps. Representing data from the database as data reduces system complexity because we don't need design patterns or complex class hierarchies to do it. We are free to manipulate data from the database with generic functions, such as returning a list made of the values of some data fields, creating a version of a map omitting a data field, or grouping maps in a list according to the value of a data field. We use generic functions for data manipulation with great flexibility, using the fact that inside a hash map, we access the value of a field via its name, represented as a string. When we package our data manipulation logic into custom functions that receive field names as arguments, we are able to use those functions on different data entities. The best way to manipulate data is to represent data as data. We represent data from the database with generic data collections, and we manipulate it with generic functions. Accessing data from a NoSQL database is done in a similar way to the approach presented in this chapter for accessing data from a relational database. With late binding, we care about data types as late as possible. Flexibility is increased as many parts of the system are free to manipulate data without dealing with concrete types. Accessing a field in a hash map is more flexible than accessing a member in an object instantiated from a class. In DOP, field names are just strings. It allows us to write generic functions to manipulate lists of maps representing data fetched from the database. In DOP, fields are first-class citizens. We can implement renaming keys in a list of maps or aggregating rows returned by a database query via generic functions. JDBC stands for Java Database Connectivity. Converting a JDBC result set into a list of maps is quite straightforward. Chapter 11. Web Services. A Faithful Messenger. This chapter covers representing a client request as a map, representing a server response as a map, passing data forward, combining data from different sources. The architecture of modern information systems is made of software components written in various programming languages like JSON, which communicate over the wire by sending and receiving data represented in a language-independent data exchange format. DOP applies the same principle to the communication between inner parts of a program. Note: when a web browser sends a request to a web service, it's quite common that the web service itself sends requests to other web services in order to fulfill the web browser request. One popular data exchange format is JSON. Inside a program, components communicate by sending and receiving data represented in a component-independent format, namely immutable data collections. In the context of a web service that fulfills a client request by fetching data from a database and other web services, representing data as with immutable data collections leads to these benefits. Using generic data manipulation functions to manipulate data from multiple data sources. Passing data forward freely with no additional complexity. Section 11.1. Another feature request. After having delivered the database milestone on time, Theo calls Nancy to share the good news. Instead of celebrating Theo's success, Nancy asks him about the ETA for the next milestone, book information enrichment with the Open Library Books API. Theo tells her that he'll get back to her with an ETA by the end of the day. When Joe arrives at the office, Theo tells him about the discussion with Nancy. Theo: I just got a phone call from Nancy, and she is stressed about the next milestone. Joe: what's in the next milestone? Theo: do you remember the Open Library Books API that I told you about a few weeks ago? Note: you can find the Open Library Books API at openlibrary.org/dev/docs/API/books. Joe: no. Theo: it's a web service that provides detailed information about books. Joe: cool. Theo: Nancy wants to enrich the book search results. Instead of fetching book information from the database, we need to retrieve extended book information from the Open Library Books API. Joe: what kind of book information? Theo, everything. Number of pages, weight, physical format, topics, etc. Joe, what about the information from the database? Theo, besides the information about the availability of the books, we don't need it anymore. Joe, have you already looked at the Open Library Books API? Theo, it's a nightmare. For some books, the information contains dozens of fields, and for other books, it has only 2 or 3 fields. Joe, what's the problem then? Theo, I have no idea how to represent data that is so sparse and unpredictable. Joe, when we represent data as data, that's not an issue. Let's have a coffee and I'll show you. Section 11.2. Building the insides like the outsides. While Theo drinks his macchiato, Joe draws a diagram on the whiteboard. Figure 11.1 shows Joe's diagram. Joe, before we dive into the details of the implementation of the book search result enrichment, let me give you a brief intro. Theo, sure. Joe takes a sip of his espresso. He then points to the diagram, figure 11.1, on the whiteboard. Joe, does this look familiar to you? Theo, of course. Joe, can you show me, roughly, the steps in the data flow of a web service? Theo, sure. Theo moves closer to the whiteboard. He writes a list of steps, see the sidebar, near the architecture diagram. The steps of the data flow inside a web service. 1. Receive a request from a client. 2. Apply business logic to the request. 3. Fetch data from external sources, for example, database and other web services. 4. Apply business logic to the responses from external sources. 5. Send the response to the client. Joe, excellent. Now comes an important insight about DOP. Theo, I'm all ears. Joe, we should build the insides of our systems like we build the outsides. Theo, what do you mean? Joe, how do components of a system communicate over the wire? Theo, by sending data. Joe, does the data format depend on the programming language of the components? Theo, no, quite often it's JSON, for which we have parsers in all programming languages. Joe, what the idiom says is that inside our program, the inner components of a program should communicate in a way that doesn't depend on the components. Theo, I don't get that. Joe, let me explain why traditional OOP breaks this idiom. Perhaps it will be clearer then. When data is represented with classes, the inner components of a program need to know the internals of the class definitions in order to communicate. Theo, what do you mean? Joe, in order to be able to access a member in a class, a component needs to import the class definition. Theo, how could it be different? Joe, in DOP, as we have seen so far, the inner components of a program communicate via generic data collections. It's similar to how components of a system communicate over the wire. Tip: we should build the insides of our systems like we build the outsides. Theo, why is that so important? Joe, from a design perspective, it's important because it means that the inner components of a program are loosely coupled. Theo, what do you mean by loosely coupled? Joe, I mean that components need no knowledge about the internals of other components. The only knowledge required is the names of the fields. Tip: in DOP, the inner components of a program are loosely coupled. Theo, and from an implementation perspective? Joe, as you'll see in a moment, implementing the steps of the data flow that you just wrote on the whiteboard is easy. It comes down to expressing the business logic in terms of generic data manipulation functions. Here, let me show you a diagram. Joe steps up to the whiteboard and sketches the drawing in figure 11.2. As Joe finishes, his cell phone rings. He excuses himself and steps outside to take the call. Theo stands alone for a few minutes in front of the whiteboard, meditating about building the insides of our systems like we build the outsides. Without really noticing it, he takes a marker and starts drawing a new diagram. See figure 11.3, which summarizes the insights that Joe just shared with him. Section 11.3, representing a client request as a map. After a few minutes, Joe comes back. When he looks at Theo's new drawing in figure 11.3, he seems satisfied. Joe, sorry for the interruption. Let's start from the beginning, parsing a client request. How do you usually receive the parameters of a client request? Theo, it depends. The parameters could be sent as URL query parameters in a GET request, or as a JSON payload in the body of a POST request. Joe, let's suppose we receive a JSON payload inside a web request. Can you give me an example of a JSON payload for an advanced search request? Theo, it would contain the text that the book title should match. Joe, and what are the details about the fields to retrieve from the Open Library Books API? Theo, they won't be passed as part of the JSON payload because they're the same for all search requests. Joe, I can imagine a scenario where you want the client to decide what fields to retrieve. For instance, a mobile client would prefer to retrieve only the most important fields and save network bandwidth. Theo, well, in that case, I would have two different search endpoints, one for mobile and one for desktop. Joe, what about situations where the client wants to display different pieces of information, depending on the application screen? For instance, in an extended search results screen, we display all the fields. In a basic search results screen, we display only the most important fields. Now you have 4 different use cases: desktop extended, desktop basic, mobile extended, and mobile basic. Would you create 4 different endpoints? Theo, okay, you've convinced me. Let's have a single search endpoint and let the client decide what fields to retrieve. Joe, can you show me an example of a JSON payload for a search request? Theo, sure. Because there's not much code, Theo writes the search request on the whiteboard. It takes very little time to show how the clients would decide on what fields to retrieve for each search result. Joe, excellent. Now, the first step is to parse the JSON string into a data structure. Theo, let me guess, it's going to be a generic data structure. Joe, of course, in that case we'll have a map. Usually JSON parsing is handled by the web server framework, but I'm going to show you how to do it manually. Theo, wait, what do you mean by the web server framework? Joe, stuff like Express in Node.js, Spring in Java, Django in Python, Ruby on Rails, ASP.NET in C#, and so forth. Theo, oh, I see. So, how do you manually parse a JSON string into a map? Joe, in JavaScript, we use json.parse. In Java, we use a third-party library like JSON. At github.com/google/json, maintained by Google. Joe opens his laptop and writes 2 code fragments, one in JavaScript and the other in Java with JSON. When he's done, he shows the code to Theo. Joe, can you write the JSON schema for the payload of a search request? Theo, sure, it would look something like this. Joe, nice. You marked the elements in the fields array as enums and not as strings. Where did you get the list of allowed values? Theo, Nancy gave me the list of the fields that she wants to expose to the users. Here, let me show you her list. Section 11.4, representing a server response as a map. Joe, what does the Open Library Books API look like? Theo, it's quite straightforward. We create a GET request with the book ISBN, and it gives us a JSON string with extended information about the book. Take a look at this. When Theo executes the code snippet, it displays a JSON string with the extended information about 7 habits of highly effective people. Joe, did Nancy ask for any special treatment of the fields returned by the API? Theo, nothing special besides keeping only the fields I showed you. Joe, that's it? Theo, yes. For example, Here's the JSON string returned by the Open Library Books API for 7 Habits of Highly Effective People after having kept only the necessary fields. Theo: also, Nancy wants us to keep only the fields that appear in the client request. Joe: do you know how to implement the double field filtering? Theo: yeah, I'll parse the JSON string from the API into a hash map, like we parsed a client request, and then I'll use _.pick twice to keep only the required fields. Joe: it sounds like a great plan to me. Can you code it, including validating the data that is returned by the Open Library API? Theo: sure. Let me first write the JSON schema for the Open Library API response. Theo needs to refresh his memory with the materials about schema composition in order to express the fact that either ISBN_10 or ISBN_13 are mandatory. After a few moments, he shows the JSON schema to Joe. Theo: now, assuming that I have a fetch response body function that sends a request and retrieves the body of the response as a string, let me code up how to do the retrieval. Give me a sec. Theo types away in his IDE for several minutes. He shows the result to Joe. Note: the JavaScript snippets of this chapter are written as if JavaScript were dealing with I/O in a synchronous way. In real life, we need to use async and await around I/O calls. Joe: looks good, but why did you add the ISBN field to the map returned by book info? Theo: it will allow me to combine information from 2 sources about the same book. Joe: I like it. Section 11.5. Passing information forward. Joe: if I understand it correctly, the program needs to combine 2 kinds of data: basic book information from the database and extended book information from the Open Library API. How are you going to combine them into a single piece of data in the response to the client? Theo: in traditional OOP, I would create a specific class for each type of book information. Joe: what do you mean? Theo: you know, I'd have classes like DB Book, Open Library Book, and Combined Book. Joe: Theo: but that won't work because we decided to go with a dynamic approach where the client decides what fields should appear in the response. Joe: true, and classes don't bring any added value because we need to pass data forward. Do you know the story of the guy who asked his friend to bring flowers to his fiancée? Theo: no. Joe takes a solemn position as if to speak before a gathering of peers. With a deep breath, he tells Theo the following story. Entranced, Theo listens carefully. The story of the guy who asked his friend to bring flowers to his fiancée. A few weeks before their wedding, Hugo wanted to send flowers to Iris, his fiancée, who was on vacation with her family in a neighboring town. Unable to travel because he's needed at work to fix a critical error in a security app, Hugo asks his friend Willie to make the trip and to take the bouquet of flowers to his beloved, accompanied by an envelope containing a love letter that Hugo had written for his fiancée. Willie, having to make the trip anyway, kindly accepts. Before giving the flowers to Iris, Willie phoned his friend Hugo to let him know that he was about to complete his mission. Hugo's joy was beyond belief, until Willie told Hugo how much he admired the quality of his writing style. Hugo was disappointed. What? Did you read the letter I wrote to my fiancée? Of course, answered Willie. It was necessary to do so in order to fulfill my duty faithfully. Theo: that doesn't make any sense. Why would Willie have to read the letter in order to fulfill his duty? Joe: that's exactly the point of the story. In a sense, traditional OOP is like Hugo's friend Willie. In order to pass information forward, OOP developers think they need to open the letter and represent information with specific classes. Theo: oh, I see. And DOP developers emulate the spirit of what Hugo expected from a delivery person. They just pass information forward as generic data structures. Joe: exactly. Theo: that's a subtle but funny analogy. Joe: let's get back to the question of combining data from the database with data from the Books API. There are two ways to do this: nesting and merging. Joe goes to the whiteboard. He finds an area to draw table 11.1 for Theo. Theo, how does nesting work? Joe, in nesting, we add a field named extended info to the information fetched from the Open Library API. Theo, I see. And what about merging? Joe, in merging, we combine the fields of both maps into a single map. Theo, if there are fields with the same name in both maps, what then? Joe, then you have a merge conflict, and you need to decide how to handle the conflict. That's the drawback of merging. Note: when merging maps, we need to think about the occurrences of conflicting fields. Theo, hopefully, in the context of extended search results, the maps don't have any fields in common. Joe, then let's merge them. Theo, would I need to write custom code for merging two maps? Joe, no. As you might remember from one of our previous sessions, Lodash provides a handy _.merge function. Note: _.merge was introduced in Chapter 5. Theo, could you refresh my memory? Joe, sure. Show me an example of maps with data from the database and data from the Open Library Books API, and I'll show you how to merge them. Theo, from the database we get only two fields, ISBN and available. From the Open Library API we get 6 fields. Here's what they look like. Joe, after calling _.merge, the result is a map with fields from both maps. Theo, let me code the JSON schema for the search books response. Here's how that would look. Theo, yes, I think we now have all the pieces to enrich our search results. Section 11.6, Search Result Enrichment in Action. Joe, can you write the steps of the enrichment data flow? Theo, sure. Theo goes to the whiteboard. He takes a moment to gather his thoughts, and then erases enough space so there's room to list the steps. The steps for the search result enrichment data flow. 1. Receive a request from a client. 2. Extract from the client's request the query and the fields to fetch from Open Library. 3. Retrieve from the database the books that match the query. 4. Fetch information from Open Library for each ISBN that match the query. 5. Extract from Open Library responses for the required fields. 6. Combine book information from the database with information from Open Library. 7. Send the response to the client. Joe, perfect. Would you like to try to implement it? Theo, I think I'll start with the implementation of the book retrieval from the database. It's quite similar to what we did last month.